So we're going to go over now independent and dependent events. So first thing we want to make sure is we know the definitions or the differences between an independent event and a dependent event. If you have two events, they're considered independent events if the occurrence of one does not affect the occurrence of the other. So whatever happens in the one event has absolutely no effect whatsoever on what happens in the second event. If whatever happens in one does affect the occurrence of the other, then it's considered a dependent event. In other words, the one event is dependent on what happens on the other. And it'll make more sense when we start giving you examples of it. So, for example, here's an event, right? Two events, and we want to know if they're independent or dependent. A box contains yellow and brown dog treats. You randomly choose one dog treat from the box, and you do not replace it. Then you randomly choose another dog treat. So event A is that the first dog treat you choose is yellow. Event B, the second dog treat you choose is brown. Now, are those independent or dependent? Well, when you look at it, at first glance, you might say to yourself, well, no, these are independent events. You pick one, it's yellow. You pick another one, it's brown. But upon further analysis of it, when you think about it, you start to realize, well, they are dependent events, because when I pick the first treat out of the box and I get a yellow treat, right, and I take it out of the box and I don't return it, when I go to pick the second time, I'm going to have less treats in the box, right, in the box, and I'm also going to have less yellow treats in the box. And so that might mean that I have a more probability of picking a different color because I have less yellow to pick from. So again, the fact that I picked from the box and I didn't replace it changed the outcome of the second event, because now I was choosing from less treats. And so they are dependent events. So in this example, let's look at another one. It says the jar contains red and blue marbles. You randomly choose a marble from the jar. Then you replace it, and then you randomly choose another marble. So event 1 is you pick a marble and the first pick is red. Event 2 is you pick a marble and the marble is blue. So again, you're trying to figure out, does the first one, picking the red marble, have any effect on the blue one? And you realize that it does not, because you picked the red marble, but you replaced it. So after you made your first choice for event 1, you put the marble back, and then you chose again. So you're starting out fresh again. Whatever happened in the first one has nothing to do with the second one. And so this would be an example of an independent event. So when we try to find the probability that an event is going to occur, given that something else has already happened, that's called a conditional probability. And we write it. So when I know something is dependent and I want to know, well, what's the probability of event B happening after event A already happened, I write it like this. So it's basically the probability of B given that A already happened. So in independent events, if I want to know, like two events are independent, event A and event B, and I want to know what is the probability that both of these events will occur, it's basically a probability product. It's the product of the probability of A happening times the probability of B happening. Because again, they're independent, one has nothing to do with the other. We'll do some examples of this. Now, when an event is dependent, then you work it out a little bit different. The probability of A and B occurring is going to be the probability of A times the probability of B given that A already happened. And again, I'll show you, it's still a product. It's just that the probability of the second event is a bit altered. Notice, the first event is always going to be the same. So let's do, and then here they give you a way of rewriting it. They say like the probability of A and B equals the probability of A times the probability of B given A. We already talked about that. And if I divide both sides by the probability of A, right, like this, then the probability of B given that A happened is equal to the probability of A and B over the probability of A. And I don't really use this formula. It's just rewriting the same thing. I always just plug it in this way, the top way. So let's kind of do some. So let's look at this question. It says, you spin the spinner shown, which is divided into 8 equal parts. Find the probability that you get, so event A, that you get a red, and event B is that you get a blue. Okay? And so if I'm thinking about this, I'm going to ask myself first, is this independent or dependent? And I realize that the spinner is independent. Every time I spin the spinner, I have an equal chance of getting the same thing I got the last time or whatever. Nothing's changed. So this is going to be, if I want A and B to have occurred, it's going to be the probability of A times the probability of B. So the probability of getting a red is 1, 2, 3 reds out of 8 on the spinner. So it's 3/8. The probability of getting a blue is a blue and a blue. There's 2 out of 8. And so the probability of getting an A and B in 2 rolls is 6. 3 times 2 and 8 times 8 is 64. And again, I can simplify that and make it, divide it by 2, let's say, 3 out of 32. So that's the probability of A and B for this independent event here. Here I got another problem. It says I have 36 green grapes and 14 purple grapes. Now together I have a total of 50 grapes. You randomly choose a grape and you eat it. So realize that means you don't return it, right? You pick a grape, but you're not putting it back in. And then you randomly choose another grape. Find the probability that both events will occur. So again, we're at the probability of A and B, but we notice that this is a dependent event. Because as soon as I pick that first grape and it's green, my probability of A, I'm going to have to do the probability of B given that A occurred, right? So the first time, the probability of A, I pick a green grape. Well, that's one green. There's 36 green grapes in the bin, and there's 50 total. So I have a probability of 36 out of 50 to pick a green grape the first time. Now, the probability of picking a green grape the second time is a little bit different. Notice that there's no longer 50 grapes in the container. There's going to be 49 grapes. And because I picked a green grape first, there's only 35 green grapes left. So the probability of picking a green grape the second time is 35 out of 49. Now, before I multiply this, if I don't have a calculator or whatever, I might want to simplify this. 36 and 50 simplify to 18 over 25. And 35 over 49 simplify to 5/7. So that's a little bit easier. And then I'm going to do the probability. So 18 times 5 is 90. And 25 times 7 is 175. And I would simplify at this point. And I get 0.514, which is 51.4%. So the probability that I'm going to get A and B in this dependent situation is 51.4% chance that that's going to happen. So again, I come here. First, I got to decide if it's independent or dependent, and then I got to answer the question. So it says a drawer contains 12 white socks and 8 black socks. You randomly choose one sock. You do not replace it. And then you randomly choose another sock. So what is the probability that both socks are white? So they want, again, event A is a white sock. Event B is also a white sock. But because I didn't replace the sock after I chose it, this is going to be a dependent event. So the probability of A and B happening is going to be the probability of A times the probability of B given that A occurred. So once again, there's a total of 20 socks. So the probability of picking a white sock on the first pick is 12 out of 20. But once I pick that white sock, I've got 11 left, and I only have 19 socks left in the drawer. So the probability of the second event is 11 out of 19. And so again, I'm ready now to multiply. Now I could simplify the 12 out of 20, and I can turn it into, let's say 4, right? 3/5. And so that's a little bit simpler. And then 3 times 11 is 33, and 5 times 19 is 95. And now I can just get the decimal or the percent, which is 0.347 or 34.7%. So the probability that both events are going to happen is 34.7. Again, I come to the next situation. It says you flip a coin 2 times. What is the probability? So again, we've got event A, that you get tails on the first one, and probability, or the event B that we're looking for, is tails on the second. And now you look and you think, is this independent or dependent? But this is a completely independent event. When you flip the coin and you go to flip it the second time, whatever you got the first time has no effect at all on the second one. So this is an independent situation, okay, this coin flip. So when you have that, the probability of A and B is just going to be the probability of A times the probability of B. So the probability of getting a tails on a flip the first time is 1 out of 2. The probability of getting tails the second time is also 1 out of 2. And the probability of getting both is 1/4, or 0.25, or 25%. So here we just have a table, and we have to kind of use the data in the table. The first one is to find the probability that a future cyclone in the northern hemisphere happens to be a hurricane. So for that, we're going to take the total of all the storms in the northern hemisphere. So we're going to add all these up and get a total, okay? So 9 and 8 is 17, and 5 is 22, carry the 2. 11, 20, 24, carry the 2. 3, 6, and 5 is 11. So for A, the probability that it's a hurricane is going to be 545 out of 1,142, which is 0.477 or 47.7%. So the answer to A is the probability is 47.7%. The second question says the probability that a hurricane happens to be in the northern hemisphere. So here we're going to look at the totals of the 2 hurricane totals. So there's 545 in the northern hemisphere, there's 215 in the southern. So total hemispheres, total hurricanes is 760. So the probability in B that it's in the northern hemisphere is going to be 545 out of 760 total hurricanes. 0.717 or 71.7%. And so the probability that a hurricane will be in the northern hemisphere is 71.7. So you just have to be careful here. What is the total that you're putting at the bottom? What's the category that goes at the bottom? And what is the event that you're looking for? And then last one we've got here. You randomly select 2 cards from a standard deck of 52. So again, you've got here 2 events, right? Event 1, or A, they want to know the probability that the first card is not a heart. So not a heart. And the second, event B, is that the second is a heart. Now, again, we've got to figure out, is it dependent or independent? Notice A, it says you replace the first card before selecting the second. So in the first one, these are independent events. In B, you do not replace the first card, so these are dependent events, okay? So first, let's figure out in a deck of cards, if there's 52, okay, 13 are going to be hearts, 13 are going to be diamonds, 13 are going to be spades, and 13 are going to be, I can't remember what the other one is, hearts, diamonds, spades, and clubs. Couldn't remember them. Okay, so the probability that something, so how many are not hearts, right? Let's just talk about that. So if you have 13 hearts, you have 39 are not hearts, right? So let's talk about the probability then. Probability of A and B in an independent event is going to be probability of A times the probability of B. So again, event A is not a heart. Well, that's going to be 39 out of 52 are not hearts. And then probability of B selecting a heart is going to be 13 out of 52. Now, 39 out of 52 simplifies to 3/4, and 13 out of 52 simplifies to 1/4. And so 3 out of 16 is the probability of getting not a heart and then getting a heart. And 3 out of 16 is equal to 0.188, or 18.8%. So you have an 18% probability of having event A and B occur on this independent event. This is when you switch, put the card back in. Now, if you didn't put the card back in, then your probability of A and B would look a little bit different. It'd be, again, the probability of A times the probability of B, given that A occurred. So let's think of the probability of A, right? Well, the probability of A is not getting a heart. Well, that's not going to change. That's still 39 non-hearts out of 52 total cards. Now, the second event is picking a heart. Well, first of all, you still have 13 hearts because you didn't pick one in the first one. Remember, you grabbed a non-heart. So there's still 13 hearts in the deck. However, instead of having 52 total cards to pick from, you're now picking out of 51 cards because one card got pulled the first time and didn't get replaced. So let me simplify 39 out of 52. That's 3/4 times 13 over 51. And so your probability of A and B without replacing the card is now going to be 39 out of 204. And when I do my probability, I'm going to get 0.191, or 19.1%. So I have a little bit better chance of getting not a heart and a heart, a little bit higher probability of getting those two events to occur if I don't replace that card. And that would make sense because, again, if I want a heart the second time and I don't replace a non-heart, I've got a better chance the second time of getting a heart. See, my probability in my second turn gets a little bit better. So again, that's my total. That's how I do it. It really, again, really matters that you recognize whether the events are dependent or independent. And then from there, the probabilities are pretty straightforward.